The International System of Measurement is a standard system for measuring various physical quantities, and we have different quantities which have actually been categorized in this system, whereby scientists came together and found it necessary to form a certain system of measurement whereby uh, everything would be uniform, especially in science and engineering. So this is grade 7 science, and if this is your first time getting into this course, kindly welcome and thank you so much for getting here. And we ask you to kindly look out for our course and our previous videos in this series so that we may move together. So let's get into it. There are different physical quantities for measuring uh, of measurement, and the first one we call them base quantities, the first level, and the second one we call them derived quantities. Base quantities were made by conventions, which are kind of agreements. As I said, scientists came together and agreed on how they would be measuring these quantities. A good example is length. They set up a standard bar which is 1 meter in size, so they just came up with a standard bar about the size of 1 foot, 1 foot apart, or kind of, and they labeled that as 1 meter, and all the other meter rules are actually replicas of that standard bar which is placed in Paris, France. So uh, we have now derived quantities which are calculated from the basic quantities. A good example is now the subdivision of that standard bar into 100 equal parts, which they called centimeters. So we normally measure in centimeters, but the SI unit of length is the meter. I have provided a list of the base quantities in this table. You can pause and look at them closely, and I've provided simple definitions, SI units, symbol, and other units. If we focus on luminous intensity, which we say is the amount of light falling on a unit area, we assume we have a point source of light, and the light is falling on a screen, and if we move the screen closer to the light, we realize that the area covered or the illuminated becomes smaller but brighter. It even becomes brighter when we move it even closer. So this confirms that the amount of light falling on a unit area, that means luminous intensity is nothing else but the amount of light per unit area. So the smaller the area, the brighter the light, and vice versa. So the other units include candela, millicandela, and all that. If we look at time, time is defined as a duration often measured by the rotation of the earth. It's measured in second, and as the earth rotates, we know that's where we are able to measure time, because scientists have already discovered that it takes 24 hours, or it takes one complete day and night, to make one complete rotation of the earth. So they divided that day and night into 24 equal parts, called it 24 hours, and subdivision of which, if you divide them by 60 and then by 60 again, you get 1 second. So this 1 second was agreed upon by the scientists to act as the SI unit of time. The other units for measuring time include the minute, hour, day, year, and all that. So you can also have a look at the others as we move on to the next one, which includes the derived quantities. I've just sampled a few of them here to help you just familiarize yourself with the physical quantities. You are very familiar with, I know you are very familiar with area, which is the extent of a plane in 2 dimensions of length, and is measured in meters squared. That is the SI unit. So what we've done here is that the length, which is just 1 dimension, is So to define an area, so that is a plane enclosed by the two dimensions for different figures. So that means it is like multiplying the one dimension of length by itself. For volume, we say this is the amount of space enclosed by 3 dimensions of length. So that means you need to have at least for the least figure that we can use or solid, we can use a cube. So if we have side times side times side, we are able to define what volume is, because it is the space actually, and it is measured in meters cubed. So the velocity is displacement per unit time, which is measured in meters per second, and all the others you can even pause and look at them one by one. Maybe I can talk about weight. Weight is the same as force. It's a product of mass and acceleration, and to be able to get this, this comes from the second law of motion, Newton's second law of motion, and that's why the SI unit for weight is actually newtons, not kilograms, newtons. So weight is actually, when we say how heavy something is influenced by acceleration due to gravity, which is different for different scientific bodies like planets, sun, moon, earth, and all that. So if you weigh a certain mass or a certain weight, sorry, on earth, when you go to the moon, your weight changes. When you go to a different planet, your weight will change, because it is influenced by acceleration due to gravity, G. Pressure is force acting normally per unit area. Its SI unit is newtons per square meter. So you see, we can have some derived units or quantities from other derived quantities. Like pressure comes from weight. So we can have some few examples. Example 1, we can do this. A box has a mass of 500 grams and measures 10 centimeters length, 5 centimeters width, and 3 centimeters height. Calculate the following quantities, giving your answer in SI units. The volume of the box, density, and the volume and density of the box. And first of all, we need to look at the box, we visualize it, and to get the volume, we have to get the 3 sides that define any space. So we have the length, width, and height, and we can now know that the volume equals to length times width times height. So the keyword here is SI unit. So we must make sure that everything is in SI units. And so now that we've been provided this in centimeters, we need to convert them into meters. That means we need to divide by 100. So make sure every dimension is in meters, and you'll be able to work out the answer well and find it to be that 0.00015 meters cubed. Density equals to mass divided by volume. Now that we have already got the volume, it's easier, because now we just need to take the mass, which is provided as 500 grams, and we convert that to kilograms by dividing by 1000, and then we just work out the density, which is mass divided by the volume, and we get that. Another example, example 2, we provided the same box with the same mass and the same length, width, and height is placed on a table. So calculate the following quantities, giving your answer in SI units. Your answers in SI units. So the weight of the box, area of cross section, and the pressure the box exerts on the table. So we need to first of all look at the box being placed on the table, and to be able to calculate the weight, we actually need to have to know that the weight of an object is acted upon its center of gravity, which is actually the centralmost point. So we assume that the mass is acting as if it was a point mass, and we get that line of action here. So all the weight of this box hangs on this point, and it's equal to mass multiplied by acceleration due to gravity. Now that this box is on planet Earth, we said the acceleration due to gravity is about 10 newtons per kilograms on Earth. So weight equals to mg, and then mass has to be converted to kilograms, and then we multiply by acceleration due to gravity, which I said is approximately 10 newtons per kilograms. So the answer becomes 1 newton. The area of cross section equals to length times width, and again we need to convert still to meters, and we get that 50 over 10,000 meters squared. And then finally the pressure of the box equals to force over area, and we already have the area of cross section. And why we use this area and not any other face is because we say that in the definition we said pressure equals to force acting normally per unit area. So the force has to be at 90 degrees with the face or with the plane of that area. So the area in contact with the, of course, the box, all the weight of the box lies on that face, on this face that is defined by length and width. That's why we use that area. So we need to be careful when calculating that area. And now that we have already calculated the weight, which is equal to the force and area here, we just need to divide them and get the answer as 200 newtons per meter squared. Now moving on to example 3, we have been given a question here. An athlete took 9.6 seconds to finish 100 meters race at a constant speed. Her temperature increased by 0.1 degrees Celsius during the race. If the athlete had a temperature of 37.5 degrees Celsius just before the race, giving your answer in SI units, calculate the speed at which the athlete raced, the body temperature of the athlete at the end of the race. To calculate the speed, speed equals to distance covered divided by time taken, and we've been given the distance as 100 meters and the time is 9.6 seconds. We are lucky this time everything is in SI units, and we just need to divide 100 by 9.6, we get 10.42 meters per second. And the temperature, to get the second one, the temperature at the end of the race equals to temperature before the race plus the increase in temperature. So we're given the increase in temperature to be 0.1, and we just add them to get 37.6 degrees Celsius. But this one is not in SI units as we've been provided. We are supposed to provide our answers in SI units. Now, what we need to do is to convert from degrees Celsius to Kelvin. We need to add 273 Kelvin. So we have 310 degrees or Kelvin, 310.6 Kelvin. End of lesson exercise. Here are some questions for you. You can attempt them during your free time, and check whether you get the answers. So the first question says, which one of the following is not a basic quantity? You're given length, mass, weight, and luminous intensity. What do you think? You can choose your answer, and then maybe then you get the answer here. So you see weight actually is not a basic quantity. The second one is a calculation question. David Kipchoge ran a 42-kilometer marathon in 59 minutes and 40 seconds. Calculate his average speed, leaving your answer in SI units. You can pause this video and then check the answer and check whether you got it right, and then everything will be okay. So here comes the answer. 10.73 meters per second. It's actually a very high speed, yeah, for a long distance. And the third one, what is the density of a block of wood whose mass is 10 grams and volume is 2 centimeters cubed. Again, give your answer in SI units. Still, again, you can pause the video and check the answer here. And now here comes the answer. It's 5,000 kilograms per cubic meters. So if you got them all right, let me know in the comment section. And thank you so much for following this lesson to the end. And please subscribe to this channel, share with your friends so that we grow together. Thank you so much.